This is the video recording for our Group 2 project submission. For our project, we decided to create a CLI program that takes in Formula One racing data, to be more specific, driver lap data, and searches it for a particular driver's ID and returns any anomalies on that driver's record. So I'll go ahead and start the program now. And we're presented with, first thing that happens is we're presented with a series of menu options. The first thing that we need to do is load the data. So we'll go ahead and load the data. And so the main purpose of this program is to search for a driver's lap time anomalies. And to do that, we're going to go ahead and choose menu option number 5 to search for scan driver for flagged laps. I'll just put in driver ID number 20. And there's a lot of data in this file. Just so you're aware, these are all flagged laps. These are not normal times, as you know, the average for that driver. These are either a fast lap, a slow lap, or an incident. So that gathers this all for us in one spot here. So we have the race ID, we have the lap ID in that race for driver number 20, and the number of milliseconds it took to complete that lap. Here we have the deviation from normal and the flag for the status or the flag for what it indicates. Here we see there's an incident. He has a significant increase in time from his average. We can also check specific laps to see just a small report of that lap itself. So to do that, we'll choose option number 3. And we're required to enter the race ID, the driver ID, and the lap number separated by spaces. So we'll use this incident as an example. We're going to put in the race ID. So the race ID is 1096. Put in the driver ID. And the lap number is going to be 26. And we'll see that we do have it was found in a linear search, it was found in the quad search, and we do see that this was indeed an incident with a deviation of plus 16% from his normal. His average is 97,000, approximately 98,000 milliseconds per lap. And here we have 113,000 milliseconds. It's important that this application be able to load large data sets quickly so that it could be analyzed to improve team performance. So we'll go ahead and run some benchmarks. And if we give this a quick analysis, we can see that we're using a number of different load factors, 0.5, 0.6, 0.7, 0.8, 0.9. We can see the number of collisions that are occurring through a linear search or linear probing versus quadratic probing. You can see the average insert times, how significantly different they are, and as we increase the load factor, how the difference between quadratic and linear probing affects the memory. And then for an even cleaner view, we can go ahead and show a results table. And here in this table, we can clearly see how much more performative quadratic probing is over linear probing and how it prevents clustering. Here we have in this capacity, if we just stick with the 0.9 load factor, we only have a capacity of approximately 600,000 spaces, and linear probing results in almost 180 million collisions, and with a 615 millisecond insert time. And if you look at quadratic probing, it's about 4.1 million versus 180 million. So it's quite the difference between linear and quadratic probing. We also see that search is not really affected by linear or quadratic probing here. It's approximately the same. And then finally, we can run some tests. And all of our tests have passed. And then we can exit the program. Thank you very much.